So I'd like to thank everyone here and the Despondé Center and Lori Pressman for all the help that they've given us over the past year. And what I'm going to talk about today is this technology that we refer to as fast flow peptides that we've invented in the lab. And really what's emerged, why we're calling this a disruptive technology, is because chemists and engineers have worked together. And what we've been able to do is we've really been able to increase the efficiency, the speed in which we can make these polypeptides. And I'm going to show you why that's important. So if you're not familiar with what a peptide is, it consists of the natural amino acids. So as shown here is methionine, isoleucine, threonine, phenylalanine. This is our favorite peptide, MIT fast flow. And so we all know about peptides. So these peptides are used therapeutically throughout the world. And some famous examples include insulin, various GLP-1 mimetics. One of the first HIV inhibitors was based on a polypeptide. It's referred to as Fusion. So why are we excited about peptides? Why do we want to transform this industry? And it's because they're in their own therapeutic class. So they're not small molecules, they're not large biologics such as antibodies, they're in between. And their molecular weights on average are between 1,000 Daltons all the way up to 10,000 Daltons. And the really nice feature about these molecules is that you chemically prepare these. So the standards and the FDA considerations are much simpler than if you work with a large antibody. And in addition, you can fine-tune these molecules if you can chemically synthesize them. So we're really interested in working with these. But if you look at the paradigm, you look at the techniques that are used to prepare these molecules, one of the major bottlenecks is the chemical synthesis. So if you use existing technologies to prepare this 5-residue polypeptide in a fully automated format, on average it would take you about 5 hours. What we want to do is be able to make this in minutes or seconds. Can we do that? And this is really the adventure we've taken with the Despondé Foundation. And to provide a starting point in terms of reference, automation in this method, referred to as solid phase peptide synthesis, led to a Nobel Prize. So there was a major breakthrough in the 60s by Bruce Merrifield, who streamlined the chemistry that's used to make polypeptides. And this generated a new industry. And the reason why is because his chemistry allows you to take common chemicals and prepare these synthetic molecules in months. And over the years, the instruments that are used actually reduce this time to hours in order to incorporate each amino acid. And he was awarded the Nobel Prize for this. And the reason why it works so well is because he narrowed down the chemistry to 4 simple repetitive steps in order to incorporate each one of those amino acids. So if you wanted to make a 20-residue polypeptide, it would require 80 steps. And this is shown here. So the first step is a deprotection. You do a wash, you do a coupling, you do another wash, and eventually you'll keep repeating this until you get the desired polypeptide that you would like to work with. And using those instruments that I had on the right, it takes a week to do a fully automated synthesis. And what we've done at MIT is we've invented this flow platform. And what this flow platform allows us to do is to really accelerate the chemistry in which is required to prepare these polypeptides. And it's quite simple. It's a benchtop unit. It's plug and play. It's fully automated. There's only 2 custom parts. And what this allows us to do, because we have specially designed fluidic manifolds, that we can then heat our reagents rapidly before they go into the reactor in order to carry out the specific chemistry that you desire. We can carry out each round of amino acid incorporation right now in around 30 seconds. So we can start to make these 30-residue polypeptides in 15 minutes rather than 30 hours. In addition, we can monitor the chemistry in the fluid profiles at a high level because we have UV detectors that allow us to watch what's going through the system. So the big question, how does this chemistry compare to the gold standard? Can we prepare peptides at the same level that exists in terms of the state of the art? And this is just showing some representative data of head-to-head comparison of state-of-the-art manual block synthesis. This is an LC-MS profile. This is a crude profile that you get when you string together all these amino acids to make this long polypeptide. If you compare it to the fast flow, you almost get identical profiles. This is another example of a shorter peptide. We can even carry out grand challenges in chemistry. Can you build fully synthetic proteins that have full biological activity? We are able to do that. So this is just two examples of proteins we prepared in the lab. This is a ribonuclease, and this is an antibody mimic referred to as the DARPin. So we believe fast flow technology is going to disrupt the industry. And one of the immediate examples that we like to point to is right now there's hundreds of companies that produce over 500,000 peptides per year, which then fuel and lead to clinical candidates. We believe with our instrument, we can have one company that supplies the world demand for custom peptides, making this truly an on-demand process. And there are other examples where people have come up with disruptive technologies as this. One example is the rate in which you can prepare oligonucleotides. Famous company is IDT. Other companies such as First Cut and Proto Labs. So at the end, we have a methodology that's faster, better, and cheaper than all existing approaches. The technology is shovel-ready. There's no extraordinary technologies or custom expertise in order to use this technology. We filed patents, and if you'd like to see some highlights of some recent news from our publications, I refer you to those references. With that said, I'd like to thank Deshpande and Leon and Lori Pressman for all their help. Thank you.